top all what we have discerned from this principle, the working stress design, and part of the CAP will be the bond splicing and among others. So pleasant afternoon, everyone. So this is CE133P-2. So at this point, we have this design of beams reinforced for tension. This can be, the beam constants are needed to be computed, and this will be set to the moment coefficient resistance and BD squared. Well, we know that R is 1 half FCKJ. That those uh, laid out parameters can be computed as one single coefficient or constant R. And then we set particular value for B as a function of D, or D as a function of B with a guiding ideal ratio of 1 half to 2/3. Then after that, we compute for the AS, the tensile requirement for this design, singly reinforced, and which is equal to M over FSJD. And then we can also obtain the magnitude, um, considering the balance still ratio multiplied by BD, that computed dimensions here. And as a function of the compressive strength of concrete, that would be FCK over 2FS BT. And then if we are dealing with design of beams reinforced for tension and compression, we start with the balance moment, which is C1J1D as MC1, and then C2J2D as MC2, or set as the compression bars. So that will be AS prime FS double prime for C2 and J2D. When, well, we can compute for the excess moment by virtue of taking the difference of the service moment and the balance moment. We divide it by Fs double prime J2D. We know that there are conditions to be set in Fs double prime as a function of FCS prime as actual compressive stress of the compression bars. And then also for the tension area, we have MT1, AS1, FSJ1D as a balance moment. And then for AS2, FSJ2D will be set as MT2. Then the difference of the service moment and the balance moment is the excess moment to be imputed in the calculation of AS2, and this must be divided FSJ2D. And then the balance can be computed. I mean, the AS1 can be computed based on this simple formula, M balance taken from this one, divided by the FSJ1D. And then we take the sum of this 2 AS. So we have this as total tension reinforcement needed at the tension area. And then we decide the stirrups, the web reinforcement, or in designing the stirrups, we need to find out the actual shear at the distance, and then we compute for the actual shear stress, and then we compare it with the allowable 0.09 square root of FC prime. We compute for the spacing of the stirrups or the web reinforcement, and then we also, by virtue of the formula AVFB, V prime BAV is the area of the utilized diameter for the stirrups. For example, 10 millimeter diameter, but this area must be multiplied by 2. That 2 has been considered as the reaction or the resisting um, vertical setup for stirrups that will mitigate the internal effect of the lateral forces manifested as tension cracks or tension stresses, diagonal stresses. And then FB is the FS, V prime is the excess shear, that's the difference of the actual and the allowable. And then B is the dimension, transverse dimension of the beam. we can compare to the D over 2 and AB over 0.0015B. And then we look for the region wherein we're going to place the syrups. And this must be the the computed value of x or region wherein the syrups must be placed. As the code recommended, we're going to add the distance from both extremities. So if you will notice at the junction of the or the intersection of the column and the beams, we have near spacing for I mean the proximity of the spacing or of the stirrups there are highly regarded, and this is very vital in the actual implementation of the design criteria for shear reinforcement or web reinforcement. And then we check for bond stress. This will be the actual bond stress, actual shear divided by the perimeter of the number of bars times JD. We compare it with the allowable band stress. In this case, this is the allowable for tension bars, allowable band stress for tension bars, 7.18 square root of FC prime over D. And then this is all allowable band stress for other than tension bars, 10.14 square root of FC prime over D. And for all compression bars, bond stress allowable is equal to 0.54 square root of FC prime. Then after that, we provide the beam section detail. Then we have this already, but I'd like to make an emphasis about the development length. So with this development length, we can anchor the idea from the point of zero moment or the inflection point where the concavity changes. So this will be the center line as indicated here. Um, from here, we have this as set up whichever is greatest among these three, D12, DB, LN over 16. And then with by virtue of this magnitude, we can say that this will be LD minus whatever governing value here. So there will be value or magnitude right here. Similar manner, whether D or 12 dB, whichever is greater, we consider that and we take the difference of it and the LD, then we have a magnitude for this one. From this point to this point to this point, we have a representation of that distance, and then we can compute for the point of zero moment. So by virtue of that magnitude, we can solve for the development. So also, we are reminded that we can extend it about 6 inches if that would be continuous in sense. So if this terminates on both sides already and there is no continuity, so there must be 12 bend here, right here, and on the other side. So this is the ACI code requirements and positive moment reinforcement must be continued uninterrupted 6 inches into the support. At least one-third simple beam, one-fourth for continuous. The negative moment, one-third reinforce of reinforcement must be continued uninterrupted by the greater of ln over 6 or the clear span over 16 or d or 12 d. So this has been manifested on this setup. So for the development length, that includes the points of inflection and the center line here. So I'd just like to be us as learning discernment that the development length plays important role in placing the main bars. For so actually this LD among other development length has been generalized as this one if you're dealing with continuous beams here. So instead of considering of the value for the development length, we can generally consider it as L1 over 4 for this first span. This will be over 3 and over 3 as well. And meaning if you are dealing with exterior support, that will be over 4. For interior supports, we are going to divide it by 3. So this will be the presentation or positioning of the main bars at if you're dealing with negative moment for the exterior and for the interior. So the cutting list must be presented just like this one. And also for the positive moment being presented as extra bars, we can have this one. And then in a while, we are going to discuss to what extent we are going to cut the remaining extra bars. But at this point, let us understand first that this must be placed directly, it must be continued here. So if, for example, you lack that particular length needed, you are dealing with 7.5 meter length beam and the commercial size is 6 meter, well, you need to splice that accordingly. So based on the recommended splice length of our National Structural Code. And also, you can, aside from using it continuously, you can employ crank bar. You can bend it up accordingly. So based on the bending situation here, in this case, that is about 1/4 of the span here, and 1/7 of the span here for bending it up. If you want it to be continuous, and as you notice here, there exists um, splice length, but the splice zone in the top bars must be somewhere here because the induced loading, induced loading actually heavily carried by the tension bars here. So the splice zone are somewhere here and within this junction. So please take note that in general we have this L/4 for exterior, and try to take a look at the bend here. That is about 12 dB. There is also an embedment length here about 40 dB to that consideration. So you already have 12 dB here, 40 dB here, and then you add the L/4. So that's the cutting length for this extra top bars at this support reaction or for that consideration. And for this interior support, you have L/3 plus the dimension of the column and another L/3. So and so on and so. If you are dealing with overhanging beam here, that's free end, so it must be bend here, and then you are going to add entirely the length from this free end to this one, dimension of the column, and then L/3. And you take notice of the positioning of the stirrups here. So the proximity of the stirrups are nearer within the area of the supports. And at the free end of cantilever beam, you will notice that we have a bit spacing on this one. In similar manner in here, and also in this mid span. Then we refer for the splicing length based on the recommending or governing code specification. Then the standard bend and cutoff points, approximate bend and cutoff points can be used in continuous beams or on the topic that we're going to discuss soon, one-way slabs where the following conditions are satisfied. Not more than half the reinforcement is bent or cut off. 2 or more spans. Unit live load does not exceed 3 times unit dead load. Loads are uniformly distributed. Spans are approximately equal with the larger of 2 adjacent spans not greater than shorter by more than 20%. And this will be the general presentation of it. So continuous bend or crank in essence. bond of reinforcing bars to the surrounding concrete influences the behavior of reinforced concrete structures in many ways. It can be a key element for the ultimate load carrying capacity of reinforced concrete structures, since it affects the anchorage of bars and the strength of lap splices. As we take a look at the bond stress slip relationship here, you take note of the three situation for the bond here: the adhesive bond, the frictional bond, and the shear bond. So within this setup for types of bond actions here, we have a mechanical interlocking that depicts the highest peak of the bond stress here. So beyond this area, it will be deformed accordingly and eventually pulled down. So that's the slip in sense of the exaggerated situation of the reinforcing bars. So the natural extent, we are actually considering bond mechanical action that interlocks, and it provides highest peak on that, for that matter, meaning highest value or magnitude. Beyond this point, it will eventually uh, torn down or pulled down. And this area is set as shearing off area, while this one is the mechanical interlocking of the bond actions. Fellow learners, bond stress slip relationship. I did presented to you this slide when before we discuss, if you will remember, prior to the discussion of the working stress design, because I want you to condition your mind that this will be the output of what we are going to deal with, whether we are dealing with working stress design or the other principle. So this will be the end result that we are going to employ, particularly in this type of structural element, beams. So there will be hooks or bend set as 12 dB right here on the support reaction, and there will be embedment length set as development length. It can be 40 dB to 100 dB, and then you add that L over 3 there, so that's entirely the length cutting list for this top bars or extra top bars somewhere here. And then for this one will be the consideration for cut-off length. If we have this as set this as this one, another 12 dB, and then L over 7. Or if the situation permits, you can also have it continuous without uh, merely cutting the reinforcing bars. The essence of knowing the cut-off points, the recommended cut-off points, is that you are actually considering um, some setup for reinforcing bars that will at least uh, provide uh, costs for or minimize the wastage of the reinforcing bars. So this minimization of the wastage transcends to the cost of the project. So naturally, we need to economize our design. That's the reason we should be adept enough or know this recommended cutoff points. And this will be the splice zone, as I have uttered a while ago. You can splice right here if you need length, additional length for the main reinforcing bars. But please take note of the splice length. It will be 40 to 50 dB. So I did present to you that this reinforcing bars here, placed here at the middle, are considered stiffeners. Actually not included in the design, or but you can also place it here, or you opt not to consider this as stiffeners. Also, for the hooks of the stirrups, it must be 6 dB. This is the beam cross section. So if you're dealing with this section, this will serve as the main bars. If you are considering this section, this will be the main bars. If you're considering this section, this exploratory section will transmit that this will be your main bars or the tension bars. I did mention about allowable band stresses for top bars and tension other than top bars and tension for all compression bars as 7.18, 10.14, 0.54 respectively. We are asked to compute the safe uniform load that the channel section shown could carry. Neglect the weight of the beam. The beam has a simple span of 6 meters. The two top bars are 16 millimeters and the four bottom bars are 20 millimeter diameter. FC is 8 megapascal, Fs is 124 megapascal. The modular ratio is 10. So we have this as 60. Normally, if you're going to place here, this positioning of the main reinforcing bars must be equally comparable in distance with this one. That's the normal setup. So if this will be 60, well, you can assume that this will be 60 as well from this edge to the center of gravity of the reinforcing bars. Well, this will be 50, the separating distance between the center of the neutral axis of the reinforcing bars in tension, and the concrete cover as well as the stirrups and the half of the main reinforcement is set as 60 millimeter as well. These are the working setup for this type of beam dimension. We are asked to investigate the adequacy. So first, by the way, in order to compute the safe uniform load here, we are going to compute for the location of the neutral axis. So we do not know exactly whether the neutral axis will fall along with this web or along with this, shall we call flange. But you can check that, just like what we did in T-beams. You can check whether the neutral axis will be located somewhere here or somewhere here. Please revisit the discussion in our T-beams. Once we know the correct assumption for the location of the neutral axis, we can then start computing the location of the neutral axis by equating the statical moment of area above that neutral axis and statical moment of area below this neutral axis. Well, for us to set it in a beam flexure theory, or for us to utilize that theory, we need to present this as equivalent concrete area for the transform section. Also for this four tension bars here. Well, you know it already that the transform section will be represented as AT prime, and that AT prime is equal to 2n minus 1 quantity times AS prime. In here, you can represent it separately, or first you get the center of gravity of it. But it will be easier if you're going to present it separately. Say you call this transform section as AS1, this one as AS2, and then you proceed with the computation of the location of the neutral axis. You will have the magnitude of the X or Y, it depends on how you're going to present that, as the location of the neutral axis from the extreme concrete compression fiber. Then from there, we can compute the centroidal moment of inertia. And then after computing the centroidal moment of inertia, we can then compute the moment capacity for concrete first, when we use the moment capacity formula for computing the concrete. And then we also make use of the formula for the moment capacity of computing the MS for steel. Well, you can utilize this one and this one. But if you have a smaller value on the denominator, it will translate greater magnitude in moment. So instead of looking into consideration of this one, you can go directly for this one as the divisor. Well, you can check that if you are already computing the Fs. And then after that, you can set the capacity, moment capacity, depends on the magnitude of these two moment capacities. And whichever is safe, meaning lower in value, that setup will be considered for computation of safe uniform load for simply supported. For a simply supported, the maximum moment is WL squared over 8. So if we have the safe moment or the moment capacity, we have the length as 6. The only unknown there is the W. So that is the time you can completely solve this number 1. For number 2, you are asked to investigate the adequacy of the beam reinforced for tension and compression as shown. The total load is 20 kilonewton per linear meter, including its own weight. And the strengths of materials are given and the modular ratios. So we are going to verify whether this setup for beam dimensions and the reinforcement here is um, sufficient enough to hold this type of loadings right here induced in this continuous beam. So by virtue of what we do in the first problem, we're going to compute for the location of the neutral axis, the, the magnitude of the moment of inertia, the values of the moment capacity, and then we take the safest moment there. This moment capacity or safe moment will be compared to the actual moment here as service moment. So you are going to employ what you discern in your structural analysis. You are going to start first in computing the support reactions here by employing techniques that you learned in theory of structures. And then once you know the support reactions, we are bound to draw the shear diagram and the moment diagram. The highest magnitude, whether positive or negative in the moment diagram, is the governing service moment here. The governing service moment will be compared to the moment capacity here. So the moment capacity must be greater than the service moment to declare it safe. Otherwise, if this one is greater than this section, you need to modify it in actual design. You need to modify your dimension, or you need to modify your reinforcement. Fellow learners, this will be your skill set enhancement undertaking to be passed within the duration. Please be back in this link. Thank you.
Recording. Recording in progress.
Dumating kayo. Kahit malakas ang ulan. Wow.
Taas ka nga, sir, eh.
Pero malakas. Sa amin malakas.
Malapit na
Hindi ko.
ngayon, sir.
So,
Sobrang dilim po, sir.
ha?
Sobrang dilim.
Sobrang dilim. Buti nga hindi nawawala yung net natin. Anyway. Sige, pakilagay na yung pangalan. Address at signature. Laki pa ng 3 tansan. Alam niyo ba yung mga galon? Dati meron pa bang galon?
Nabutan ko sir.
Labo na. Okay. Ibang tanong, may tanong ba? May clarification? May kulang na ng attendance kasi 44, 38 lang to. Huwag naman kayo dumoble pag nakapag-ano na kayo. Kulang lang siya. Check nila, baka hindi pa kayo, may mga pumapasok. On video lang, saglit lang, mga auto records lang. Souvenir ko lang, piniprint ko to, tapos nilalagay ko sa wall ko. Tingnan lang. Tingnan lang natin yan. Best smile, mga auto, request lang. Teka muna, may nag-key in pa ng name. Hindi makita si Okay. Kompleto na, mukhang kompleto na. Okay, saglit lang to. On 3, smile lang ng konti. On video nga lang, tol. Request lang, hindi ko nababanggit yung pangalan niya. Para, okay. Pag wala hindi gumagalaw, alam niyo na. Nagme-merienda, iniwan tayo. Okay. Papa, thank you. May iba pa bang tanong? Kung wala, I'm going to let you do the SEU. But before you do that, allow me to share this one. Sinare din sa akin to. Experts and other specialists believe that our subconscious mind is powerful and can, without our awareness, direct the course of what we do in life. One of the authors of the Chicken Soup for the Soul, Jack Canfield, insisted that we must learn to choose our thoughts effectively because our thoughts, both conscious and subconscious, due to the law of attraction, are what creating our current experience of reality. This includes our level of success in every area of our life. Soon you will have work, you will have business, you are going to set solid financial life, relationships, health, and happiness, among others. We are asked to make an overhaul. Let us anchor our subjective maps of reality to the most delighted ones. Let this fears be changed and capitalized as fulfilling excellence in areas robust specialties. Let these beliefs mirror greater inclinations of reality. Lastly, let these memories articulate you to a more discerning individual. Napakadali sa akin ang iusal ang mga ito kasi, well, I am grateful na hindi ko naranasan yung may mga iba sa inyo na nakakaranas ngayon ng pinag-uusapang sakit. Pero ang tanging pwede kong maitulong ay yung unang-unang marapat na maitutulong. Hindi man financial, pero yun ang pinakamalakas na tool. And in these challenging events, through these unfortunate times, it is true, paglabas natin dito, nag-face-to-face tayo, we have to start from scratch, kahit na yung mga business and entrepreneurs. So they have to start from scratch. Pero the greater truth to begin with is we have to end to begin. Mga utol, pag nilay-nilayan ninyo yan, at naniniwala akong sa kabila ng lahat ng ito, ay napaka-grateful pa rin tayo dahil marami pa rin tayong pagpapasalamat. Be humble, be safe, be blessed. Bye-bye. SEU, mga utol.
Thank you, sir.
Sige, sir. Kaya